Welcome to this lab alternative for Activity 2.2 out of our PS2 book. Just one of the things I want to update you on is our book has changed a little bit this year, the formatting. So the page numbers should line up, but in the future, if you're doing this lab and you're listening to this video, if the pages don't quite line up, the questions are there. It's been reformatted, so the pages might not line up, but yet all the questions are there. You just have to find a correct page and it can be done. If you have any questions, just make sure you ask me in class. So our learning target today is we're going to practice doing an experimental design, a fair test. And we're going to talk a little bit about what goes into a fair test. And I might say, okay, if I was gone and I have to redo this, why do I have to listen to all this? Well, this is going to be the basis of a lot of stuff we do this year. We want to make sure that the tests are fair. We want to make sure that every group gets similar data because they're doing things consistently. So the expectation for you is you need to be able to identify the key components of a fair test and use those components in your experiment. Now, one of the things you need to know, and you're going to need to know today, is what is the difference between an independent variable and a dependent variable? So independent variables are the variables that you change or manipulate. Today it's going to be speed, and it's also going to be mass. So we'll talk about that in a little bit. The dependent variable is what changes as a result of you changing or manipulating the independent variable. So we're going to talk a little bit about that later too. The controls are very important. These are the things that must remain constant or things that don't change. So every team in here, every group needs to be consistent with these controls. If not, your data is going to be wrong. And in science, we want to control all these so we have really good results. In today's activity, again, if you're doing the alternative, obviously you're not going to be using the Play-Doh. But what the students did was they created 30 millimeter Play-Doh balls. And what we're going to do is we're going to drop cans on them from various heights and various weights. Actually, the height's not going to change. It's always going to be 30 centimeters. But we're going to drop a large can and then we're going to toss it to change the speed. And then we're going to drop the light can and the heavy can to change the mass. So the drop height will always be 30 centimeters. And in part one, we're going to use the large can. In part two, we're going to use both the large and the small. So again, it's important to do the same things each time so that not only your results are the same as every other group, but your 3 trials are the same as well. So in part one, what we're going to do is we're going to drop a can on a clay ball to investigate the relationship between the speed of a moving can and the amount of kinetic energy it has. Then what we're going to do is we're going to do 3 trials. We're going to do 3 more trials. But this time, the book says throw, but we're actually going to toss it. We're going to push it down. In other words, we're going to manipulate the speed. Now, the height remains constant, but we're going to change the speed, and we're going to see how it impacts kinetic energy. Now, kinetic energy, how do we measure that? Well, there's different ways you can measure it, but we're going to take a very basic approach here in class. What we're going to do is we're going to take a look at the deformation of the clay or the Play-Doh. I know this is clay, but we switched to Play-Doh. So in other words, how much squish did that 3 centimeter or 30 millimeter Play-Doh ball get? So when you drop the can, if it was 30 millimeters to begin with, what is it at the end? And theoretically, the more squish you have, the more kinetic energy it was subjected to. So that's how we're going to indirectly measure kinetic energy in here. So what do I need from you? The first thing I need you to do is go to page 9. Again, the pages may vary depending on what year you're doing this lab alternative. But go to page 9 and you should see predictions. Go ahead, read this over, and then pause the video to make a prediction. How does the speed of a moving object affect the amount of kinetic energy it has? Then in a sentence, describe the evidence you need to collect to test your prediction and include a reason why you think this evidence is necessary. The second part might be a little bit more challenging because you're not actually doing the lab, but based on my description, you should be able to answer that. But I'm really looking for a good prediction from the first part. So go ahead, pause the video, and then start it when you've written your prediction. All right. So the next thing I want you to do is if you turn the page over. Oops, sorry, there's a lot of lines there. What I want you to do is fill in this data. So we started with 30 millimeter Play-Doh balls. What we did was we took the can and we just dropped it. We just released it onto the Play-Doh from 30 centimeters up. And what we did was we measured the Play-Doh ball after the can hit it. So here's trial number 1. We started with 30, and then it was 23 at the end. Trial number 2 for the dropping was 30, and then it was 22. Then it was 30, then 25. The second time through, even though it says throwing, we basically tossed it. In other words, we took our wrist and then we pushed the can down, still from 30 centimeters. But what it did was it increased the speed, so we had the slow and the fast. Started with 30, now we ended up with 10. We started with 30, and we ended up with 12 and 11. So the amount of squish, how much squish was there? So go ahead and calculate these numbers. In fact, what I'm going to do is I'm going to change these numbers right now, because these were actually the numbers over here. So let's work backwards. If those numbers are here, what was the amount of thickness afterwards? Well, if you started with 30 and you had 10 millimeters of squish, what number should this be? If you said 20, go ahead, put 20 in here. How about if we ended up with 12? What should this have been? Well, 30 minus what equals 12? If you said 18, you're correct. And then how about 11? 30 minus what equals 11? If you said 19, you're correct. So we just went through the math for this. Now, can you figure out what these are? Yeah, take 30 minus 23. That's your answer for here. 30 minus 22 is your answer for here. And 25, or 30 minus 25 is your answer for here. And you should definitely notice a difference. That these right here, the amount of squish is less than these. So you're going to need to know that, because the next thing I want you to do on the bottom of page 9, again, the page numbers may vary depending on what year, is what I want you to do is take a look at this and tell me, oh, I'm on the wrong spot. You should actually be on page 10. It says, for the first data, describe how the dependent variable changed when you changed the independent variable. So remember I told you we were going to talk about that in a little bit. So when we look at these two things, the dropping of the can and the throwing of the can, is this going to be your dependent or independent variable? Now, if you said this is your independent variable, you're correct. This is what we're manipulating. We dropped it, so it went slow at first, and then we tossed it, and it went fast. So if this is the dependent variable, this is the independent variable. If I said dependent, I might have. This is the independent variable. This is going to be the dependent variable, because the faster you throw it, you change this changes. So theoretically, the faster you throw it, the more squish you're going to get. So go ahead and answer, just in a sentence or two. For the first data, describe how the dependent variable changed when you change to independent variable. So now let's take a look at part 2. Again, you're not actually going to do the lab, but we're going to talk about it. So in this one, we're going to drop the light cans. We have 2 different cans. We're going to drop the light can onto that clay ball or that Play-Doh ball. Then we're going to go ahead and we're going to drop the large can. We're still going to go from 30 centimeters. We still have a 30 millimeter Play-Doh ball. So what's changing here is the independent variable. And the independent variable here is going to be your mass. We have the large can down here and we have the small can. So what I want you to do is make a prediction. How does the mass of a moving object affect the amount of kinetic energy it has? So just give me a sentence. And then if you can, based on what we talked about, describe the evidence you need to collect to test your predictions and include a reason why you think this evidence is necessary. So go ahead, pause the video, fill this out, and then hit play when you're ready to go on. So what I'd like you to do is go ahead and fill out the data table. And the next thing we're going to do, again, we drew the lines in here. So you don't have those in yours, go ahead, draw the lines. So let's record the can. So the light can was 170 grams. The heavy can was 425 cans. So go ahead, record those 2 measurements. This is also a good check to see if you're listening to me or if you just have the video on mute and you're not actually putting anything in here because you won't see it. So go ahead and calculate these based on what we talked the last time. Take 30 minus this number to get this. So go ahead and do your calculations. Now you should have noticed a difference. Just like before, you should have noticed that the independent variable, which is the mass of the can, as this changes, so does the amount of squish. And the squish is the dependent variable. It's dependent on the size of the can. So go ahead, and this should be on the top of page 11. Again, the page numbers may change depending on where you're at, what year you're doing it. Is for the second data, describe how the dependent variable changed when you changed the independent variable. So go ahead, write a sentence or two, pause the video, and hit play when you're done. The next thing I want you to do is the making sense questions. And these making sense questions are going to be on page 11, and there's also a question on page 12 for you. So number one, how does speed affect the amount of kinetic energy in a moving object? Explain how you know by stating a claim, the evidence for your claim, and your reason why this evidence supports your claim. So what I like you to do is go ahead and write a mini CER based on your data. Now, I'm not going to show you the answers for this, but when you get done, come up. We can take a look. I can look at yours, and I can let you know if you did a really good job. Or if you're gone and you have it done by the time we go through it, you can check to see if you did a really good job. So when we look at the next question, it's for the second activity that we did. How does the mass affect the amount of kinetic energy in a moving object? Again, I need a claim. What evidence do you have? And what's your reason why this evidence supports your claim? So here's another mini CER. So this should be a good sized paragraph. You cannot do this in a sentence or two. And the very last thing I want you to do is when you flip the page over, Luis and Keisha each drop stones from different heights onto pieces of clay to see how much the clay would be compacted. Luis dropped his stone onto a small piece of clay and noticed that the clay was smashed a lot. Keisha dropped her stone onto a large piece of clay and noticed that the clay was compacted very little. Should Luis and Keisha conclude that Lewis's stone had more kinetic energy when it hit the clay? Explain why. So go ahead, pause the video, answer this, and when you're done, hit play. So what we learned today was that all moving objects have kinetic energy, or KE. And KE is dependent on speed, and it's dependent on mass. So add these to the front of your boat, your book. Not, I was going to say your boat, but your book. Kinetic energy, if you want to just say KE, is dependent on speed and mass. And then we're going to add one scientific principle today. Number one, we already added. So if you were absent and you didn't have that, make sure you add that. But number two, an object's KE increases as its speed and or mass increases. Now the opposite is also true. It will go down if its speed and or mass decreases. But here's a caveat right here. As long as the other stays constant. So if speed decreases, KE decreases as long as mass stays the same. But if one goes down and the other one goes up, it could actually offset each other. So I wanted to make sure you understood that if one goes down, yeah, KE is going to decrease as long as the other one stays constant. And that's going to be huge to truly understanding that. So once you get done with the lab, if you want to show me, we can go through it. We can talk about it. We can make sure that you understand the concepts taught here. So that way, if any of these questions are in a test, you know what the correct answers are. Also, make sure if you were doing this to get caught up, make sure you let me see your book so I can check it off as being done if you have missed a book check because of missing this lab. Thanks. Bye.